Hello, everyone. Uh, Welcome to the fourth lecture of Operating Systems Engineering. In this class, we'll be looking at process synchronization. So, a brief review of previous lecture. In the previous lecture, we saw what is a process and what are the benefits of process isolation. Basically, this provides uh, an abstraction for each process so that the process need not worry about memory that it accesses. And it also provides security that we'll be looking into later. That's Those are the advantages of process isolation. And we also looked at process state transition diagram where process goes through various states depending on its current task. For instance, the process could be blocked or it could be terminated or it could be ready or it could be running. And we also looked at process control block, which is and PCP is a short form of it. And we also saw what are the things that are stored in process control block, specifically uh, process management info, memory info, and also input output information. And we also saw why we need concurrent processes, basically to effectively utilize hardware resources. Uh, if you have multiple CPUs, it's better to have processes running on each CPU at the same time to make to make effective use of the CPUs. And we also looked at mechanisms to create, process, and terminate. Like specifically, we looked at various examples of forks, and we also looked at exec, which actually replaces the entire memory of running process with a given process, with a given program, rather. So, so in this class, we'll be looking at synchronization. So synchronization is a mechanism uh, to ensure that multiple processes are executing as expected. And and to do that, like we also need to do CPU scheduling, like because when we have only one CPU, and especially in case of multi-programming operating systems, we need to switch a CPU, like we need to switch different processes, in which case we need to pause the current process and start another process, right? And an important question in case of multi-programming systems is when to schedule. So what is the right time to pause the current process and start another process? So let's look at the simplest scheduler. Like when do we want to pause the running process and like rather do the scheduling, right? The simplest scheduler is called one way in which we can do the scheduling is non-preemptive scheduler. Like this is one of the most um like oldest or rather the simplest scheduler we have seen in the operating systems, and it's actually used in old systems such as Windows 3.1 and Mac OS. And in this scheduler, what happens is, so here the process gets scheduled only if the current process doesn't need the CPU. So if a process needs the CPU, it's always running. However, when a process doesn't need the CPU, and it will be paused, and other process that needs a CPU will be scheduled onto the CPU. And in this method, there is no timer because we don't give any time to the running process. Rather, we wait for the process to run or like to make sure that it's not uh, it has finished its job, because we only schedule when the current process doesn't need the CPU. So there is no need for timer. And this scheduler, I mean, it performs three things. One, it saves the current process state, it chooses the next process to run, and it dispatches. An important thing that this scheduler needs to figure out is when the current process doesn't need the CPU. How does the scheduler know that the current process doesn't need the CPU anymore? So the process doesn't need the CPU in at least two cases. In the first case, if it is blocked on some input output or some other resource. For instance, the process could be blocked because it is waiting for network packet arrival, or it could be blocked because it's waiting for input from keyboard, or it could be blocked because it's waiting for disk operations to be completed. In other case, a process may actually give up the CPU voluntarily. This can happen when the process knows that it is waiting for some other process, or it is waiting for some network server to finish some job. So a process can act nicely and it can actually give up the CPU. It can actually inform the operating system it doesn't need CPU anymore. And this this is usually done through a system call. It's commonly called as yield. So when you call yield, your the process is actually informing the operating system that it doesn't need the CPU anymore. So this is how we know that the process doesn't need CPU. And let's look back to our friendly's transition diagram of a process when the process goes through various states. So when the process, we know that the scheduling decision happens, like the scheduling happens when the process is running, right? So when scheduler kicks in, it actually pauses the running process, and it takes the another process, and it runs it. So when a current process is running, when does the scheduler kicks in? So let's say when the current process is running, it can either terminate, or it can be blocked, or it can go to ready state. So there are three transitions from a running process. So a process can give up the can inform the operating system that it doesn't need the CPU. So it can call yield, in which case it goes to ready state, and the process will be paused, and another process will be scheduled. And the process can actually terminate. Basically, it finished the execution of all the instructions, in which case, of course, the process doesn't need the CPU anymore. Of course, the scheduler comes in and schedules another process. The process may be blocked because it's waiting for resource, in which case, again, the scheduler will come in and it will pause the running process and it schedule another process. So how does a process terminate itself? So we are in the last class, if you remember, there was an example where we have used a system called exit. So exit is a system call through which a process tells to the operating system uh, to to terminate the current process. And now that we know when the scheduler kicks in, now let's see what happens during scheduling. So when process needs to schedule, so it has to do two things. First, it needs to save the state of the current process, or rather old process, and then it needs to load the contents of the new process to be run onto the CPU. And this process is also called context switching. Like, it's commonly referred as context switching. And what are the things that, like I mentioned, that it needs to save the state of the process, right? So what is the state of a process? So as I mentioned in previous lecture, operating system maintains process control block, PCB, that saves the entire state of the process. Specifically, uh, it has a process control block has process management info, which contains various CPU registers and various other scheduling information. And it also has memory management info and IO management information. So now CPU, or rather scheduler, needs to save the state onto the process control block, and then get the process control block of the new process and read the state from the process control block and then schedule it. So if we look at the timeline diagram of context switch, so this is how it happens. So let's say process P1 is executing, and let's say it yielded the CPU, or it informed the operating system that it doesn't need CPU anymore by using a system call, in which case operating system saves the state into PCB0, the PCB of P0, and then it reloads the state from PCB1, assuming there are only two processes in the system, and it reloads the state from PCB1 and it starts executing P1. And when P1 yields the CPU back again, then it saves the state again to PCB1 and it reloads the state from PCB0 and starts executing process 0. So this is how the context switch happens in principle. And you can imagine that this scheduling could happen multiple times, right? Whenever processes uh, yield CPU or when they are blocked. And a brief detour. Uh, so in case of multi-programming, you can actually have the memory requirements of the of all the programs could be more than the available physical memory. So, uh, for instance, I actually showed an example in the class where you can have like programs which actually request for memory, which is more than the available physical memory, right? In which case, what happens specifically? Like, imagine if there are three processes A, B, C, and the memory requirement of all the three processes combined is actually more than the physical memory. So it cannot store all the three processes in the physical memory. Then how does process restore, or rather save the state of the process when there is no physical memory available, right? So the technique operating system uses, it uses disk. So it's usually called swap space. So instead of storing the contents into the main memory, it actually stores the PCB into swap space. Rather, it's a specialized partition on the disk where the process control blocks will be saved, because there is no memory available. So instead of pressuring the memory, it will actually save the process control block onto the disk. So this is called swap space. And we'll be looking into more details of what swap space is and how it is managed when we discuss virtual memory later in the course. Now let's get into process synchronization. So as I mentioned before, when there are multiple processes running in the system, then we can have a requirement where processes may want to communicate with each other by using shared data, right? The shared data could be either from shared address space or through shared memory objects, which we'll be looking into more details in when you do lab 2. And then process may communicate through files. Basically, one process may write to a file, the other process can actually read from that file, right? And there is also message passing mechanisms which operating system provide that can be used to send messages between processes. And let's ask ourselves a question, like, what happens if multiple processes try to access shared data at the same time, like concurrently? So uh, imagine there are processes running by two siblings, and at 3 p.m., let's say a program kicks in and the program actually checks if balance is greater than 10, then you withdraw $10. So imagine if these two instances of the program runs at the same time at 3 p.m. So you can see that you can actually withdraw more than, like, two siblings might simultaneously withdraw the money, because when they run at the same time, you can imagine that so since balance is a shared variable, when they access both at the same time, they can actually both see that the balance is greater than 10 and they withdraw 10. So we could withdraw more money than what is expected. And how to ensure uh, that the communication happens properly, like how to ensure that the shared data is actually modified in a sensible way, and how hard is such a solution? So let's look at a more concrete example where, let's look at a real world example. Let's say we have two persons in a house, and let's say we want to make sure that we always have milk in the house. So uh, so person A comes and he comes into the house. He opens the fridge and sees that we are out of milk. And person A leaves for Walmart And then when person A leaves for Walmart, let's say person B comes to the home, and like she opens the fridge and she figures out that there is no milk because and then she also leaves for the Walmart, and when they come back later, they have more milk than what is needed. So this is a simple example of too much milk problem. So how do we solve this? I mean, this is a common problem that happens in most of the households, right? How do we solve this? If you remember, the way we solve this is we use sticky notes. So we usually, whenever we go out to get milk, we usually write a note on the refrigerator saying that I'm going out to get some milk. So this works perfectly, right? So when you see there is no milk, you usually look at the refrigerator, and if there is a note, you know that one person has went out to get milk, so you don't buy milk. So there is no more milk than needed. However, such a solution will not work in processes. The reason is, imagine instead of person A, person B, if these are two processes, so we can have, because of how these processes are scheduled, we can have uh, like the numbers indicate the order in which the instructions are executed on the CPU. Let's say first process A, which stands for person A. So process A comes and it executes instruction one and instruction two, like first two if statements, and then it gets scheduled, and the process B comes in, which also executes first two statements. Okay, in which case both the conditions are true. So now let's say process B gets scheduled and process A comes, and then it's already inside the if, and then it leaves the node, and it buys the milk, and it removes the node. However, process B, when the process B gets scheduled, it's already inside the if, so it also leaves the node, it also buys milk. So this solution doesn't work if used in real processes. However, how does this work? If you think about it, it works so well when we actually use when we are real persons. But when we replace persons with processes, this doesn't work. The reason for this is not the highlighted instructions. So these are the two instructions that actually control the decision of buying the milk, right? And the reason it works for human is because human can actually test and set at the same time. What that means is, so when a human is looking at the refrigerator and is testing for the milk on the person, and when we leaves the note, and the other person cannot come in, because if the other person comes in, human can know, and he can not set the note. So basically, uh, the testing, or basically checking of milk and leaving a note, are atomic. They are performed as a single unit. So, but this is not possible in processes because of scheduling, where we have granularity of instructions. So the scheduling can happen in between of test and set. But that's not the case with humans, because test and set happens at the same time when humans are when we replace processes with humans. So another possible solution is as shown on the screen. Let's use two different nodes. Let's uh, let's use node A, node B, and let's node A belongs to person A, node B belongs to person B, or rather two different processes where node A belongs to process A, node B belongs to process B. Here, uh, when process A executes, it actually leaves node, process A node, and then it checks if there is no node from B. If there is no node from B, then if there is no milk, then it will buy the milk. And then at the end, process A removes the like the node from process A. Similarly, process B has its own node B. So whenever it wants to check the milk, it leaves It leaves the note by setting node B, and then it checks if node A hasn't put any note. If not, then it will check if there is no milk, then it will buy the milk. I mean, this solution kind of seems uh, this seems to work, right? I mean, but there is a problem with this solution. Like if you want to figure out what's the problem is, you can pause the video for a couple of minutes and think through the solution and see what is the problem with the solution. The problem with the solution, like if you have figured out the problem, then very good. So the problem is we may have the other problem of not having milk. Basically, imagine when two processes like process A and process B, when they come in, imagine they execute each instruction, like the instructions are interleaved one at a time. By that I mean, let's say process A comes, it leaves note A, and let's say it gets scheduled, and process B comes in, and then process B also leaves note B. Okay. Now let's say now it doesn't matter who gets scheduled. Now let's say process A gets scheduled again. It sees that a note from process B, so it will not go into the if. It will come out and it will remove note A. Similarly, process B, it checks if there is no note from A. However, process A already put the note, so it will not enter the first if, and it will come out and it will remove note B. So we may not have the milk, right? So let's think about another solution. So another solution, I mean, actually, like using two nodes works well, but the only problem we had was there was a case where when both of them execute at the same time, then we may not have milk. Let's try to avoid that. One way to avoid that is as shown on the slide. So here, let's say process A, when it leaves after leaving node A, it actually waits until node B is not set. If the node B is set, it will just do nothing and it will wait till node B is not set. And when the node B is not set, then it will check for the milk. If there is no milk, it will buy the milk. Similarly, process B codes remains unchanged. It doesn't use while loop, whereas it will leave node B and it will check node A. If there is no milk, it will buy the milk. And if you see, this solution actually works. This solution, using this solution, there is no way, I mean, we'll always, if there is no milk, either process A or process B will buy the milk. And if somebody else buys the milk, uh, we don't have, we have neither of the problems, right? We don't have more milk. We don't have less milk. Rather, we have a right amount of milk. So what's wrong with this solution? Or rather, why, like, can this solution be better? Or rather, what is what is something that you don't like about this solution, if there is anything that you don't like? So me personally, this solution works, this solution is fine. However, I don't like uh, I don't like the thing that the code of process A and process B is so different, right? uh, i don't like I don't like the code to be different. I would rather want the same code to be used in process A and process B, rather than using different code. Like, because process A has to do the while loop, process B has to do if. I don't like the solution because the code is different. And yeah, I mean, uh, that's the same thing. It's like, it's too complicated. Imagine two processes, it's fine. Imagine if there are multiple processes who in that case I need to use different codes for different processes, and it soon gets out of control. And also, one thing to note here is when process A is actually busy waiting, right? When process B leaves node B, process A is just doing nothing. It's just looping. It just as you can see, the while loop, it's just looping without doing anything. It's basically wasting CPU cycles. We don't want that. Ideally, what we want is, I'm sorry. So we need to have a mechanism to acquire, let's say there is a function call which says which is acquire lock, which actually allows you to enter into the, like, if the lock is acquired, then you can continue. If the lock is not acquired, you just get stuck there, and you can release the lock. Once you acquire the lock, you can release the lock. And what we want from this uh, lock acquiring and releasing is, we want to make sure that the code where we check for milk and where we buy the milk is actually executed by only one process at a time. So it doesn't matter how many processes we have. Whenever we want to ensure that only one process can ever check for the existence of milk. Okay, so this is called critical section. So, and to do that, we need help from operating system and also hardware, right? And let's see let's formally define what we mean by critical section. So a critical section is a section of code, or rather collection of operations, in which we want only one process to be executing at any given time. So we can define a set of instructions, and we only want we only ever want one process to be executing that section of code. In case of multiple processes uh, sharing the same code. And uh, and mutual exclusion is a mechanism which is provided by the operating system to ensure that only one process or one person is doing certain things at a time. So mutual exclusion, you can use mutual exclusion to protect critical section, right? So mutual exclusion enables you to make sure that only one process can be executing certain set of instructions, and then if those that particular set of instructions can be critical section. So example of critical sections are modifying concurrent access to the shared variables. Basically, if a variable is used by multiple processes, then any access to that variable should be considered as a critical section. Or rather, if all the processes are actually reading the variable, then it's fine. However, if at least one process is writing the variable, then we want that variable, or rather, we want access to that variable to be considered as a critical section. Because if every process is only reading a variable, it doesn't matter. However, if one of the processes is writing a variable, then all accesses to the variables should be considered as critical section. And as I mentioned before, mutual exclusion is a mechanism provided by the operating system to ensure that only one process can be executing certain set of instructions. So such a mechanism should be fair. By that I mean, if several processes are waiting, then each one of them should eventually get an opportunity to execute critical section. And it also should be efficient. So we don't want to use the loop, rather, like, we don't want to do busy wait. I mean like, we don't want to check the variable in a loop constantly, right? We don't want to do that. So, and we also want the mechanism to be simple to use. Rather, we should be able to just have our set of statements and then enclose them in braces and just use some annotations and call it critical section, and operating system should somehow ensure mutual exclusion of those particular instructions. So it should be fair so that all processes get an opportunity to enter the critical section, and it should be efficient so that we don't waste CPU resources. And finally, it should be simple to use. And how to achieve mutual exclusion? We use locking. So, so as the name suggests, so only one person or rather one process can have access to the lock. So, and so whenever we want to execute certain set of instructions in critical section, we must use the lock. So only one process can actually lock, can actually perform the lock. And and after after locking the critical section, it executes the critical section, and at the end, it needs to unlock so that other process can take the lock. And finally, if the lock is already held by some other process, then any process that is trying to acquire the lock should wait. So these are the three fundamental properties that we want from any locking mechanism. And furthermore, the processes, when they want to use mutual exclusion supported through locks, so they always need to lock, they always need to acquire the lock rather, uh, or rather, like instead of the, process needs to acquire the lock before manipulating shared data, and then after accessing shared data, it should unlock the lock. Okay, and then we should not lock the we should not lock already locked if the lock is already locked. What that means is, imagine we should not have two calls to acquire lock sequentially, because I mean that can lead to deadlock, because the process can be waiting for the lock that is held by itself. So we'll be looking into more details about deadlock uh, in the next class. And if you did not lock the if you don't ha- if you haven't locked the lock, don't unlock it. And then just make sure that don't spend you don't spend large amounts of time in the critical section. Basically, when you have held the lock, don't try to do large activities, or rather uh, time consuming tasks when the lock is held. So, and the way mutual, as I mentioned before, the way mutual exclusion is provided by the operating system is through locks. So, so locks can solve simple problems. Of course, there are other ways in which mutual exclusion is provided, like semaphores and condition variables, monitors, and we'll be looking into them more in the next class. And then note that each of these primitives are kind of are atomic, in the sense uh, acquiring lock is an atomic event. That means, so you can consider that as a single assembly instruction, or rather single CPU instruction, and you cannot do anything. You cannot like have half lock acquire. No, you can either acquire the lock or not acquire the lock. You cannot have half acquire or half release, because these are atomic operations. And the way these are provided is by using these special hardware instructions called test and set. So hardware provides these, for instance, x86 has test and set instruction, using which operating system provides the logs and other mechanisms. So the way, I mean, this is a simple example of a lock acquire and lock release. So where inside the lock acquire, you can imagine like this is a simple implementation of lock acquire. However, in reality, this is not how it will be implemented. But in principle, you can imagine that in case of lock acquire, you see if the lock is already held. If it is held, you just block or you just wait. And then once you know that lock is released, you decrement the lock to make lock 0, which indicates you have acquired the lock. And then the lock release will actually check if the lock is held. That means when lock is 0, and if it is held, it will just increment the lock to notify that the lock is released. So initially lock will be released. So when the value of lock is 0, that means the lock is held, and the value of lock is 1, that means lock is free. And note that, as I mentioned before, each of these primitives is atomic. Like, ignore the code that is inside lock acquire and lock release. But when you call lock acquire, so the entire operation is atomic. And the way it is made atomic is whenever you call lock acquire, so if you are blocked, then operating system knows that you are blocked, and you will be put your state of the process in the process control block will be made to sleep, or rather blocked, so that you will only be scheduled when the logs on which you are depending on are available. And so yeah, let's visit our too much milk problem again. So here, let's say one way to do this using locks. Imagine acquire lock is lock acquisition and release lock is releasing the lock. We just acquire the lock. If there is no milk, let's buy milk. What is the problem with this solution? And if you want to think about it, you can again pause the video and see, like, I mean, this looks fine, right? It actually solves the problem. However, there is a subtle issue with this problem, with the solution. The thing is, we are actually buying the milk by holding the lock. However, as we saw in the like couple of slides before, we really want to avoid doing tasks that need more time inside a critical section. So we don't want to buy milk inside critical section, because buying milk might take more time, and it could actually cause a lot of processes to be blocked. Because once, let's say, when the process decides to buy milk, it can it can just let the other process run, right? Rather than uh, other process needs to wait till this process buys the milk. So we don't want to spend large amount of time inside the critical section. Basically, we don't want to buy the milk after holding a lock. We don't want to do that. So how can we solve this? So one way to solve this, I mean, if you don't understand the code, please ignore. We'll be going through the code in more detail in the next class. But we can use multiple variables, or like multiple shared variables, to only set the flag inside the critical section. And however, we can buy the milk outside the critical section. Here you can see that there are two critical sections, the top one and the bottom one. In the top one, we set two variables, that is note and local flag. Then in the bottom critical section, we also just check variables. We check the variables and we set few variables. Then you see that buying milk, which is actually a heavyweight task, is actually outside the critical section. So it only happens when local flag is false. And if you analyze the code carefully, you will see that this code actually ensures mutual exclusion. At the same time, it also ensures that we don't spend a lot of time inside critical section. So don't worry if you don't understand the code. We'll be going into more details in the next class. So to summarize, uh, so a good process synchronization mechanism should have three properties. The first one is correctness. So we should ensure that only one process should be inside a critical section. And here, this property should be independent of the CPU speeds. So we should not be making any assumptions on the CPU speed. And this should also work on multiple processors. Basically, it should also work when you have multiple CPUs that are running your code. And finally, we should also make sure that the synchronization mechanism is efficient. Basically, it has good performance. And we want to make sure that processes do not wait indefinitely. Like this property is called bounded waiting. Basically, we should have an upper limit of when a process will get a chance to execute the critical section. And we should also make sure that the processes that are outside the critical section should not should not affect the code that is running inside critical section, or rather anything that controls the critical section should not be uh, should not be done by some process, or rather should not be done by the code that is running outside critical section. And finally, it should be easy to program. I mean, if you make it hard to program, definitely it'll make it makes it really hard to like when you make something hard to program, it basically opens chances for programmer errors, and consequently you'll have many bugs, and you actually lose the cause. Basically, you lose the reason why you started this, right? You eventually want developers to use your synchronization mechanism. And one of the important things to ensure that developers use your mechanism is to make sure that it is easy to use, or rather easy to program. Reading assignments for the next class, please read Dinosaur Chapter 6, Process Synchronization. It has various examples, and it explains the concepts that uh, we have looked at in this class in more detail. And if you don't have Dinosaur book, don't worry, read chapters 26, 28, 29 from Comment. Thank you.